and welcome to the Sustainable Design Special Interest Group webinar series. My name is Daniela Pigoso, and I'm the chair of the Sustainable Design Special Interest Group, which is actually only one out of 16 different special interest groups in the design society. Our main goal in the group is to understand how we can develop sustainable design methods and transfer them to industry so that we can come up with more sustainable products and services. A little bit about the Design Society before we move any further. This is a worldwide community of academics, but also industry people, which has the goal to understand how to design solutions to complex problems. Right now, we are more than 800 different members across 50 different countries. There are several different initiatives in the Design Society, including conferences, webinars, special interest groups, and so forth. And I really invite you to have a look into that if you have interest in design, design science, and also design practice. Our website is designsociety.org, and there you can find all the information about the society and the ways to engage as well. But I don't want to take any longer. I actually want to introduce you to Yann Leroy, that is going to be our speaker today. He's going to talk about changing end user behavior and how we can use that as a lever towards a better sustainable performance. Yann is an assistant professor at the Industrial Engineering Research Department at CentraleSupélec in France, and is also a member of the University Paris-Saclay. He has a PhD in Industrial Engineering and also a master degree in Industrial Ecology from the University of Technology de Troyes. Yann is one of the members of the Sustainable Design SIG, and his research and teaching activities are focused on sustainable design, circular economy, and also environmental assessment of systems. Yann, it's really nice to have you here today to share your insights about changing end user behavior, and the floor is yours. Thank you very much.
Thank you, Daniela. Hello, everybody. I'm pleased to be here for this webinar, and that's the subject of my purpose is all. We have to consider end user behavior as a lever toward better sustainable performance. As you can see on the picture, we need now to accompany end users for design activities toward better integration of environmental protection and green behavior. But it's not so easy because people are quite different. We can identify a lot of variability between people. Sometimes they don't know how to choose between investing in specific equipment instead of another. If one behavior is better than another one. Obviously, there are several equipment that are quite useful for such decisions, such as smart metering, IoT, but sometimes it's quite difficult to take the good decisions without the knowledge. Why focusing on end user behavior? Because we think it's a strong part of the way to reduce greenhouse gases, for example, or reducing our raw material consumptions. Recently, consultant company in France estimated that we can reduce greenhouse gases emission by up to 20% solely adopting the right and green behaviors. So let's move to an example. I'd like to present you a specific work we performed several years ago, maybe 5 years ago, with my colleague Bernard Yanou and Toufik Zaraket. We also pursued with new territory and new company. around an activity-based modeling framework for quantifying occupants' energy consumption in residential buildings. So the motivation is the following. We choose the building sector because in France and in Europe is one of the major contributor to greenhouse gases emissions. Sorry. As you can see on this picture, in France, focusing on residential buildings and personal buildings, we consume for more than 40% of our production of energy. So reducing energy consumption also contributes to reduce CO2 emission of buildings and goes to sustainable environmental. Few years ago, so France decided to adopt new regulations, first to promote sustainable construction, to establish new labels and regulations around energy consumption, and to incite users through tax reduction to reduce their energy consumption. Facing this problem, constructors has new, I'd say, also behaviors in design. So they decided to integrate more environment in their design product developments to go to green buildings, but also to shift from product to service to guarantee energy efficiency. Moreover, and it's maybe the main point they had to tackle a few years ago, the authorities decided to impose a control of the variability of energy performance to engage company in delivering buildings with high performance energy. If the performance are not reached, it may occur penalties, economic penalties for these owners. Oh, sorry for that. So if we look at the design determinant that play a big role on energy consumption buildings, we have for first physical properties, obviously, the installed equipment and systems. We're talking about heating, essentially. We have the climate, but also we have occupant behaviors. Or looking at physical properties, we have the location, altitude, surface area, orientation. As you see, for installed systems, we have HVAC, but hot water also, procurement and lighting, and so on. Occupants' behavior is a bit complicated because usually it's play a big role while people are at home because of the presence, but also through their intentional activities that mix interaction between occupants, but also appliance they embed in the dwelling. So occupants' behavior is very complex phenomenon to address. Why it is complex? Because we have a high variability of occupants' behavior coming from income, diversity of profiles, the number of occupants, obviously, the family types, the age, the education level. As we assume that the more, the highest the education level is, the more aware about environmental protection you are. The social professional class also. But this diversity is also combined to diversity of appliance type, but also the ownership rate. Looking at the incomes is a big variables, allowing people to buy a specific appliance with a high environmental performance. And all these attributes to the profiles conduce to diversity of energy consumption patterns. And looking at the literature review, sometimes we have energy consumption variation that can reach up to 100%. That is very high. So the problem might be stated as following. For the industrial context and motivation of brick construction, which is the owner and the construction company, They usually use energy simulation tools to simulate energy performance in building before constructing and delivering buildings. But the main problem is that they usually use a conventional scenario. Let's say the same profile for each household and each inhabitant. So in this context, it is quite difficult to engage the company on a specific energy performance contract, having this very high variability in energy consumption. So the goal to reach is to gain more precise method for modeling occupants-related energy consumption for developing green residential buildings. So we need more accurate predictions. We need to refine energy guarantee performance, but also improve service offers. If we look at the literature review, usually simulating energy consumption is used to estimate energy demand. So in a very early phase of design, to identify possible energy saving, which is more dedicated to the end users and occupants, to monitor energy consumptions, and also to evaluate energy efficiency program and promotion campaigns. Different techniques are usually used, as you may know. Well, the first one is bottom-up. So we use data collected by individual dwelling levels to determine relations between the household characteristics and energy use. We can put in this trend all IoT solutions, or maybe automation also. The other one is very top-down, as we use a high-level data, such as national energy statistics, to derive causal relationship between energy consumption and its determinants. Following on the literature review, there are two main strategies to go into such simulations. The first one is to deploy time-use survey, which is really quite time-consuming because we have to enter into the dwelling, ask our question, gather all information, and did this. And usually we use Monte Carlo's Markov chain. The main problem with this is first is time consuming. The second is that using Monte Carlo Markov chain limit the assessment because this kind of tools have no memory. So if we look at the activity cooking, after cooking you hit what you have cooked. The Monte Carlo Markov chain may conduce you to cook a new lunch maybe 2 or 3 times a day. So it's not very relevant for our case study. The second one is to deploy artificial intelligence for multi-agent systems. So this is a picture of several works that was done in Electricité de France. So they try to use multi-agent system and develop a gameplay such as maybe you know The Sims, in which occupants navigate into the dwelling, perform activities, and in real time we have the energy consumptions. But the main difficulty is we have complex occupants, cognitive behaviors, and it's quite difficult to learn. So the research gap is no model-driven approach of occupant energy consumption. We have rough characterizations of household attributes. We have a high variability assessment, which is not possible, and we have also a problem of reliability of data sources. So if we look more in details in our case study, we have the building for first, which is first determinant of the energy consumptions, essentially because it embeds heating, cooling, ancillaries. Most of the simulations are driven by software such as Terensys. We have the dwelling, which is more about shared, let's say, functionality or features such as lighting, refrigeration, domestic hot water, but also electric heater and coolers. And the last part is is the occupant's daily activities, for which we have intentional domestic activities that are performed to answer specific needs. This is the main scope of our study. If we look at the activity type, that was our first, let's say, breakdown. We identify the major activities that are related to identification of appliances that are used to perform such activities. But also we found that activity is sometimes different by nature. Some of them are quite additive, watching laundry activity, for example. Some others are shared by people living in the dwelling. Watching TV, for example, but also using the light is shared, and sometimes it's very difficult to analyze. So to quantify energy consumption, the hypothesis we formulate is we derive the concept of functional unit that you can find in life cycle assessments to embed it into our framework. So an example for eating activity, the service unit might be the number of meals or the quantity of meal per day and per person. So you can see there in the table several activities and service units we derived for our model. Watching TV is sometimes shared and additive. We address the durations, the time, people watching TV. For basing, this is more additive activity. It's essentially the number of showers took by people living in the dwelling, and so on. The main hypothesis we formulated is that the total energy consumption is the sum of energy consumption per activity. So we have an additivity formula for each activities. But also the total activity quantity per household is an additive energy consumption per individual for additive activity, and an aggregations of energy consumption per individual for the shared activity with respect to the service unit per activity. In that sense, we identified and modeled 28 domestic activity. Looking at this picture, we have all entertainment, looking at TV, playing a video game, cooking, washing dishes, texture, and so on, communication. Yeah, let's go in the modeling framework. It can be represented as so. So what's very interesting for us is in the blue square. So the need should be satisfied by an activity, and this activity is performed through an actions that involve both the end user, but also the appliance with regard to the service unit. So external parameters might be the external environment, the climate area that influence the need of the individuals, but also the building characteristics, the nature, the location, the surface that also influence the need. And these building characteristics also influence or constraints the appliance, the ownership of appliance, the energy class of the identifications. Household profile can also be characterized by individual profile attributes, such as the age, the gender, the activity status, job or jobless, the social professional class, the education level, but also the income. And all this individual profile can be aggregated into a household profile that defines the need for the household. And yeah, once the need is qualified and quantified using the activity in the service unit, we can perform the action and calculate the energy and water flow for the realization of such activities. To do so, we use Monte Carlo simulations to have a stochastic energy consumptions. Yeah, as you can see, you'll find the informations we use to feed our model. So for the individual profiles, we use national statistics from INSEE, which is the French National Institute for Statistics. Gathering incomes, number of occupants per kind of dwellings, the family types, the social professional class, the education level, the age. For the appliance, we use several studies for, again, National French Statistics Institute, which is INSEE or CREDAC. And we use national statistical, sometimes heuristics, to define the service units to fit the activity and quantify the activity. So we develop a stochastic activity model based so-called Supélec. The first input is the diversity of user profiles that is defined through individual attributes, also household attributes. These attributes help us to define conditional probability to perform an activity, a quantity of activity per household, and a specific pattern of using appliance. Also, for the appliance part, the conditional probability help us to define the rate of ownerships for appliance, but also appliance characteristics. We address for equal level with a good appliance and less performant appliance. So the energy consumption activity is run by Monte Carlo simulations, which something quite interesting is that the 28 domestic activity are quite interrelated. So sometimes it's quite easy from one or two activity to calculate and simulate the performance for others. This is what we call cascading of service unit. For example, if we look at how works laundry and washing clothes, when you wash the clothes, we have specific parts we have to dry, and this part dried should be also ironed. So it's, if we have the function between the different activity, we can form a first proxy, redefine the service quantity and service activity for this different activity. So this is an example of the Supélec applied to watching TV activity. Though we chose this activity because it was one of the major electric consumer in the dwelling, more or less 11%. In France, there's an increasing possession rates because of the multiplication of screen in house. We also have a large variety of appliances, maybe 3 or 4 a few years ago, and also a diversity of consumption patterns. So the service unit we use is a watching duration per individual and per day, and this activity is a shared activity. We limited the use of TV only to watch channels, but also to watch DVD and video. We excluded the surf on internet streamings, video gameplay, and listening to the radio. So we, for first, have to define a given household, which have its own attribute per individual or for the household itself. Now, using the conditional probability, we have to define if the household have or not TV. If it have TV, we go further and define the technology related to the TV and its energy efficiency through eco-label. All these informations are extracted from National Institute of Statistics. For the same given household, we also have to define the TV watching duration per individual or for the household. So we based our heuristics on the National Statistics Institute. And as you can see, according to the profession, the social professional class, the time watching TV is quite different in terms of minutes per day. As the activity watching TV is shared between people living in the household, we also introduce a sharing coefficient per individuals, also derived from national statistics. So obviously for a single person, the coefficient is null. And for a couple with children, the coefficient is more or less 0.7. And finally, we ran Monte Carlo simulations to obtain the distribution curve of energy consumption in terms of kilowatts. So this is an example of result we can obtain using the platform. Here we have the simulations for specific household. The number of runs was efficiently used to obtain robust information. So for a single people, as you can see, we consume very less than couple with 3 children. So using this kind of modeling, we can have, or we can predict, forecast the energy consumption for a specific household over a period of 1 month of 1 year. What we can also do with the platform is to constrain the simulations. For this first time, we constrain the household type. And as you can see, we can capture the variability of energy consumptions. Or we can also constrain the household types and the number of children, or the number of persons, which is one of the major contributors or determinant in our energy consumption pattern. Now, if we look at the model validations, we unfortunately we didn't have time, neither means to equip several households. So we use 2 studies about an ERTEC and Remodes project, and we compare our simulations to real data coming from a national household. So finally, we find that our simulations are quite similar to this real data that we gathered, which provide us a good first step toward validations. So finally, we defined this SABEC framework and defined also a platform to simulate household and their activities, and 28 activities. Doing so, we allow reconstruction to refine thermodynamic simulations and embed new or add in into TNCs to refine the individual and household profile. And finally, using or refining such simulations, we also allow us to refine the energy performance contracts. We also used such analysis of consumption patterns to develop a guidance for choosing technical solutions, but and choosing between individual solutions or shared solutions. So the first example is to pre-install washing machines, shared washing machines in buildings that could reduce the energy consumption for this activity, especially by more than 70%. And finally, we also improve the information feedback systems or qualifying informations, then with construction use into its service offer called Energy Pass, which is a smart monitor giving information in real time. So if I conclude this presentation, the takeaway might be as follows: we addressing end users behaviors and understanding their behaviors, we have the opportunity to maybe decrease up to 20% the greenhouse gases emissions. This 20% was derived by a specific French consultancy office. But we also have to, this kind of model can also provide us better understanding of energy consumption patterns, but also better understanding of impacts of occupant activity. So using IoT or using a smart meter, we have a real-time energy consumption, which is more an aggregation between all activities and clients. Using such breakdown, we can put or define the main cause of energy consumptions. Using so, we can also help identifying abnormal energy consumption patterns in a specific household or residence, and its cause. So might be the individual or household behavior itself, might be a defect of the appliance that might require more maintenance or equipment substitutions, but also might be the affordance and the interaction between those two. So for me, the main challenge now accompanying end user toward more green behavior is more than monitoring energy consumptions using IoT smart meters in real time. Defining the real cause might help them to define the real lever to accompany end user in their daily life. Another point that we pursue this work with Paris-Saclay territory. And another good point or point of interest we identify is that we really need to disseminate informations and vulgarize informations to end users, because they are aware of the environmental issues. There are a lot of solutions that are offered to perform their daily life activities, but they do not understand how to minimize their energy consumptions or maybe their water consumptions, because they do not understand what's the main cause of such impacts. And finally, such information coupled with life cycle assessments or environmental accounting might be useful to develop, let's say, green incentive or nudge, to accompany again the end users. So I think it's okay for me. Feel free to.
Wonderful. Thank you for your presentation, Yann. It's now time to the questions, and we have received a number of questions already. If you have additional questions, just add in the box, and then I'll come back to them. But I've structured the questions in three main areas. The first one is about modeling. The second one is about how to use the results. And the third one has to do with decision making. So if we start with the first area, that is about modeling. The first question that we have here from Sophie, she asks whether you have also included passive activities in the modeling, such as charging mobiles, electric cars, and so forth.
Yes, thank you, Sophie, for your question. So if we go back to the slides, we restricted the study to the household. So we excluded the building and shared equipment. So for charging cars, for example, is quite excluded from the studies. But for your computer or smartphone, IoT equipments, we also integrate them into the activity and its descriptions. It might be connected to the appliance, what we call appliance or equipment. So if you need to perform an activity to satisfy a need, we include all electric appliance equipment, you need to realize it.
Perfect. Thanks for that. Yeah, and the next question is from Yuri, and he asks whether you have considered people's profile features in relation to how important is sustainability by them.
Yeah, thank you, Yuri. Yeah, we tried to include this in our study, but not in a direct manner. First, we didn't know how to enter such parameter in the model. So we decided, or we find a proxy, which is might be discussed, but we connected the education level to the awareness of environmental protections. The more the education level high, I assist your awareness about environmental issues.
Yeah, and I think in connection to that, we have a question from Steve, and he's asking whether you have explored the rebound effects that could be linked with change of consumer behavior when, for instance, using more efficient products.
Not directly, not specifically in this study. But you're right, Steve. What we observe is that our framework can capture the energy consumption patterns, but what about using, let's say, an automatic laundry out of your dwelling? We cannot capture this kind of consumptions. If we were a lot of in lockdown these last weeks, so we cooked a lot at home. But what about calling Uber Eats? And because all the energy consumed to prepare the meal is dedicated or allocated to the company or the restaurant, and not for the home. But this is a good question. We try to address it in a new project with the Paris-Saclay territory. And we try to combine 60 households into being more, being greener in several aspects: biodiversity, mobility, local procurement, and so on. And indeed, there are a lot of interactions and potentially rebound effects, trying to greening a specific activity for a specific environmental impact.
Great. And then I have a question in relation to the actual results that you have obtained with the modeling. Is that right to say that sharing washing machines could save 70% of energy? And how is that possible?
Yeah. The simulation I've done that. It's I'm not sure, but I think we also introduce there's a specific choice of appliance, of type of appliance, to be more robust because it's more intensively used by people in the dwelling. So we also reduced I'll say maybe appliance with eye defects and so on. I was very surprised a few months ago because I discussed with a specific groupment of washing machine producer, and they say that more than 70 to 80% of the park, of the entire park of washing machine in France, is running with defects. So we overconsume, we overeat, but we also overconsume water. So entering such shared washing machine conduces us to produce more robust appliance. And this is not my facts or our own simulations, but Bouygues Immobilier, which is a specific company, or let's say this is the same group of Bouygues. Bouygues Immobilier now sell pre-equipped household effectively to reduce this variability and ensure the respect of the energy performance contract.
Mm-hmm. Yeah, and I think it links very well to the third block of question that has to do with how do we use the results from the modeling to actually change end user behavior. So the first question here is, for instance, if you have identified that TV has a big energy use, what strategies can you use to convince people to reduce it?
It's a tricky question because we made our research in engineering field, but your question also relied to the social field, and might be not the good example watching TV, because in recent social studies we can find that entertainment, TV, and so on is part of the freedom area of people. So they are more reluctant to change their habits. But what we tried a few years ago is to smart meter energy consumption in student residence. And through a challenge, we asked them to try to reduce their energy consumptions. And we highlight that fridge and the share equipment were the main consumer. And what we also identified that some of them were obsolete, so they were over consuming, and they really have to be changed to first work well and to participate to this energy consumption. So to get back to the example of the TV, might also be guidance or let's say guidance to invest in new TV according to your need, according to your activity, and so on.
Mm-hmm. And we have a question connected to that as well from Anya. She asks, what motivational factors do you know to make end users more aware of their energy consumption?
I think there are two specific levels. We conduct this work with weak constructions, and finally the results were used by engineers to fit their dynamic thermic simulations. But we find a good hearing while discussing with owner of social buildings. So the level might be the economic consequence of reducing your energy consumptions. The other way is to give opportunity to people already involved or that are aware of environmental issue to go further in their daily activities. In our new project, we observed that a lot of people are aware of this environmental issue. They are aware to try to invest in new technology or to try new or to change their behavior, but they don't know how to do. A funny example is about, you may know about compost. On territory, a lot of people invest, so they pay so they buy a composter, they put it in the garden, they feed the garden all the year, but finally they don't know what to do with the compost. So I point out a lack of knowledge, a lack of informations about what specific behavioral consuming patterns may imply for environments.
Mm-hmm. And we have only time for one final question, and this is related to how can we use all the knowledge that we have obtained through these modeling activities to actually design products and services that will help to minimize the overall consumption. How to use all of that in the design process.
Well, the first thing is, if we go to the example, is to make product more robust. In our case, we make the building more robust to end users' behaviors and users' profile. Might also be useful to develop reconfigurable products, maybe, that might be, let's say, adaptable to the change of behavior, the change of family type, the change of number, or maybe the less outcome. I don't know what. The last thing I think, yeah, might be to develop product that induce a green, let's say, a green affordance, green or good affordance, because most of the marginal energy consumption or environmental impacts comes from specific usage for which the appliance or the interaction was not designed.
Mm-hmm. Wonderful. Thank you very much for that, Yann. It was really nice to have you here sharing your research on user behavior.
Thank you.
Thanks everybody for coming and for sending questions and comments to Yann. I'd like to use the last minute to invite you to our next webinar, which is going to be just after summer in October, where we're going to discuss how users perceive the sustainability performance of products. Yuri Borgiani from Italy has been done some very detailed research studies and surveys to try to understand what's the connection between product features and user understanding of enhanced sustainability performance. So I hope you'll be able to join us in October. And then during that webinar, we will also be announcing the new series for the autumn, where we're going to have lots of other experts, mainly from industry, sharing their insights on sustainable design and how to develop more sustainable products. I hope to see you there. In the meantime, have a good summer or a good winter, depending on where you are. And we hope to see each other again in October. Thanks a lot, and we keep in contact. Bye-bye.